So hello everyone, welcome to this video. In this video we will be learning about the attention block in Edison transformer. So this is a continuation of video on patch embedding. So let's get started. So a quick recap of everything that we learned in the patch embedding video. So we learned that we converted an image into vectors to represent a particular patch of an image. And the flow of how we created a vector was we had an image, we broke that image into n p cross p patches, and each individual patch has 3 channels, and we flattened those channels, and then we use that flattened channels and subjected it to a linear matrix multiplication to obtain a vector embedding. Then we added the position embedding to it to get the final embeddings, and the final embeddings are E1, E2, E3, E4 and En. So this was what we learned in our previous class. Now in this class we will be learning about how these embeddings E1, E2, E3, E4, E4, E5 can be connected to each other to give the model, the context of each patch with respect to patches in its surrounding. So we are trying to make each individual embedding contextually aware so that model can understand about the context of that particular patch. And in this video I will be implementing a different strategy since it requires a good understanding and theory of attention. I will be using whiteboards to first lay the foundations, and then we will proceed towards the presentation and animations. So let me share the whiteboard. So yeah, now let's dive into the actual concept of transformers attention. Sorry. So as I said, attention is used to get contextual rich embeddings. That is, communicate between embeddings. So how can we achieve this? Let's try to learn from a first principle approach. So we want to ensure that these embeddings, for example, these are our embeddings. We need to ensure that E1 is contextually aware about E2, E3. How can we make this? So yeah, so let me give you an example. For example, this is a graph, XY graph. We know that a line, this would give us a relationship between X and Y, right? We are relating two variables X and Y. How? We are relating it like this: Y is equals to mx plus c. So we can use this knowledge, like we know that we need a function or a relation to connect many variables, right? So what if we have something like this for these embeddings as well? Something like this: e1 equal to something coefficient e1 plus something coefficient e2 plus something coefficient e3. Would this be a good way to relate these embeddings? What do you think? This is simple, right? So would that be efficient? Yeah, it would be efficient. So this is how we relate embeddings. This is how we give model the context. We are trying to make the value of e1 by forming it with other these values. Okay, so how can we find the value of these coefficient? Another concept again. Think of these two vectors, a vector, v vector. If the angle between them is theta, how can we find that these two vectors are similar in context and dissimilar in context? We can find it by finding the dot product, a dot b. Let's see this, a dot b cost. And this is the formula, right? We know that if two vectors are similar, we know that the value of theta would be small, right? If the value of theta would be small, the value of cos theta would be greater. As a result, A dot B would also be greater. So we can imply that if A dot B is great, a big number, the two vectors are similar, related. And if the dot product of two vectors is a small number, we can imply that the two vectors are dissimilar to each other. So this is a really simple concept that is being used in transformers attention mechanism to find the coefficient of these. It's really simple, right? So let me rewrite this again with mathematical clarity. E1 would be, what is this? E1 dot product E1 multiplied by E1 plus E1 multiplied by E2 dot product multiplied by E2 plus E1 dot product E3 multiplied by E3. You might be confused, right? But it's really simple. What are we? Look at this in the example. A dot B. We're trying to find the similarity between A and B, right? So what does this do? We are trying to find the similarity between E1 and E1. Since we need to find the value of A, right? What is our value? This E1, E2, E3. So we need to find the value of these dot product of these two vectors. And again, E1, E2. We are trying to find the similarity score between these two. Again, E1, E3. Okay, it's really simple. So this would give us the contextually aware embedding, and this is what is happening in um, attention block in a transformer. But there are some things that there are some things that I need to teach you guys. Once you look into this more clearly, you see that this is a simple mathematical process. Simple math. There are no learnable things, right? No learnable parameters. As a result, we cannot use gradient descent to optimize our result. These are simple maths, so there are no learnable parameters. As a result, we cannot apply stochastic gradient descent and different algorithms to optimize the value of embeddings and optimize the output. So this is a drawback of this self-attention. So we need to introduce something that would give us that would give the model the flexibility to change the value and optimize the output. So what we do is, instead of using these E1, E2, these values, these are the same embeddings that we got from the patch embedding block, right? So instead of using the same value in three different works, once you look closely, you would see that there are a single embedding is being used in three different ways. Here, here, and here, right? It is being used in three different places. A single embedding E1 is being used, the same value of E1 is being used here three times. But what if we could ensure that the same value is not used and a more optimized value is used here? So this was why we introduced query, key, and value. what we do is we have an embedding. This is our embedding. We generate three different values from this single embedding, that are query, key, and value. This was our initial embedding. So how do we do this? What we do is we have this embedding E. We multiply this with three different learnable matrices. This solves the problem that I said earlier, that the model could not optimize the values in this embeddings to optimize the output, right? So what we do is we introduce three learnable parameters. These are three learnable matrices that is multiplied to this embedding: WQ, WK, WV. Then we would get Q, K, and V. And how do we use this Q, K, V? Let me write. What were the three things that the embedding was being used on? First, what value is the subject? With which are we comparing the similarity score? The question, that is the query. The question, what are we finding similarity with? Second, what are we multiplying the query with? What is the other thing that we are trying to find the similarity score with? That is the key. And what are we finally multiplying the similarity score with? That is the value of that embedding, right? So these are the three places we are using the embeddings, and these are query, key, and value. And how do we use that? We use like this: query times k times v, that is multiplication. Let me write like this. This is how we are using query, key, and value. But once you look at the actual paper of transformers, the formula is a little bit different. Let me write that formula as well. Softmax, query times keys transpose by root dimension of k multiplied by v. So this is a little different from what I just wrote this. So let me explain what is different and what is happening here. So let's start with this upper term. What I wrote query dot product k. What is this? This is query multiplied by key vectors, matrix transpose. So these two terms are equivalent. Let me prove it. Suppose we have these a dot b, and suppose a vector is a row vector and b is also a row vector. So we need to show that this is equivalent to a vector multiplied by v vectors transpose, right? So let's compute this value first. Suppose this is a1, b1, c1, a2, b2, c2. How do we calculate the dot product? We just multiply the corresponding elements, right? a1, a2 plus b1, b2 plus c1, c2. This is the value of dot product. And let's compute this value. What is A matrix? It is A1, B1, C1. Can we multiply this? The shape is 3 cross 1. So what is this? This is the transpose of this matrix A2, B2, C2. The shape is 1 cross 3. So we can multiply it, right? What is the value then? It is A1, A2 plus B1, B2 plus C1, C2. Aren't these two terms equivalent? Yeah. So this formula is valid. So now you should have understand that this is equivalent to this dot product. Don't get confused. This dot is multiplication, and this dot is vector dot product. So now we are done with the upper part. So why divide by dk, and what is dk? So dk is the dimension of key vector. it is the dimension of key vector, and we divide it because to attain, we need to understand that what is happening upstairs in above this. We are multiplying, right? Multiplying, if we multiply two values, there are number of values, right? For example, there are 768 dimensions in each vector. In each vector there are 768 dimensions. We are multiplying each elements, right? So as the decay increases, that is the value of 768 increases, we choose a number like 880, the variance in values obtained after multiplication also increases, and we divide with decay to ensure that the rise is not very big and is in a certain range. This would ensure a better performance on the algorithms of optimization like stochastic gradient descent. This would make the process of training more efficient and faster. So this is why we use decay, divide by decay. Okay, now we have also finished this. We finished this Q part, upper part, the down part. Now this softmax. Let me first draw an example. For example, this is an image, patch P1, P2 and P3. So what will we have? We will have an embedding of each individual one, right? What we do, we find the query, key and value vectors of each individual ones. Query 1, key 1, V1, query 2, V2, key 2, V2, query 3, key 3, V3. So you need to understand that the matrix, transformation matrix that we are using here are the same. Okay, why same? To make the process computationally efficient and cheap. Okay, so these are q1, k1, v1, q2, k2, v2, q3, k3, v3. And again, let me write the formula that I first wrote. Suppose e1 is an embedding, we write e1 plus e2 plus e3. You can see there is a plus, right? And there are values and coefficients here. So why do we need softmax? Is to ensure that the value of these coefficients lie in a certain range. The range is 0 to 1. Why? Because we know that the value of dot product ranges from belongs to real number, right? So the value can be anything, really big. So this could cause computers to break down or the training process to halt. So we need to ensure that the value is in some small range so that the multiplication that happens to the embeddings is not really big and is computationally efficient. So we need softmax to ensure that the similarity scores are in a certain range, and the sum of each and the sum of all the coefficient similarity scores is equivalent to 1. So why do we need softmax? To ensure that the coefficients value is in a range, not minus infinity to infinity, but 0 to 1. Okay, so I was explaining like here. Let's get back to this image. I would be explaining about how do we use that softmax properly. If q1 is this, we would use it would be something like this, right? K1, K2, K3. There would be a matrix V1, V2, v3 like this. So the value would come like something like this. These are the similarity scores, right? So we take these values and put it through Softmax and get the values, and we use these values and multiply it with the value vector, that is v. Okay, so this is what is happening in an attention module. So in summary, attention is QKV is Softmax, QK is transpose, this is multiply root dk multiplied with v. So this is the main formula of Softmax. And after this, we need to know about a concept that is required. That is multi-head attention. Multi-head attention. So what is multi-head attention and why do we need multi-head attention? So why? First, why? We need to know that when we multiply the vector with query key and value vectors, so query key and value transformation matrix, we are converting the values of embeddings of that particular patch to fit in particular tasks, right? But we need to ensure that the same patch could be represented in different forms. Like a particular patch should have different aspects like color, shape, orientation, different aspects. But the process we are doing, the query key and value vectors multiplication, is an average process, not a specific process. For example, when we apply that, we are not specifically looking at the color aspect of that particular patch, not the shape aspect, not the orientation aspect. Rather, we are looking at that image in an overall view. So this would result in model not getting perspectives from different fields, right? This would restrict the model's perspective to be a single. But we need to ensure that the model is sophisticated enough to understand that image from all the different perspectives. So we need to introduce multi-head attention that would allow model to see that particular patch from different dimensions and make the model sophisticated enough so that when a user inputs an image that is really hard to understand, the model would be able to understand. So this is why we need multi-head attention. So how do we achieve multi-head attention? Let me show you. So let me go back to a process. So this is our embedding matrix, right? Where each row is an embedding of a particular patch. The shape would be, and that is the number of patches, and G model. That is the dimension of a particular patch, which is optimal value. So this is 768 for our case. So what do is we multiply this with what? With WQ, WK and WV. Why? We need to obtain the query key and value vectors, right? So query key and value vectors. The shape of this would be D model, comma T model, okay? And this would be the same shape. Query would be the shape 7, 768. That is N, T model, and the same for these also. So what do we do in this multi-head attention is that we break this query key and value vectors row wise, column wise, into H heads. Do you understand? We break this query into different, for example, for a particular head, for example, for head H, we divide it 768 by 8, and each individual head would use query's value as n comma 768 comma 8. This would be the shape of the query of a particular head. Same for key and value. Same for these. And we follow the same pattern that we were following before. Self attention would be query, key transpose, root decay, V, and softmax. The same process after this splitting into head. And after that, what we do is we will add values from different heads, right? From head 1 this would be, from head 2 this would be the result, from head 3 this would be the result, and from h head n this would be the result. What we do, we concatenate these all, we stack them together, and after this we multiply it with a learnable matrix to do a learned feature extraction that ensures all the dominant and good features are represented in this. This would be the summarization from different aspects of the patch. What we do, we multiply it, learn transformation matrix. So what would this be? This would be the summarized embedding of a patch from different dimension. So this is the overall flow of the attention block in a visual transformer. Now I guess I have laid the foundations required for understanding from the presentation and slides. So let's move back to the slides. So everything that I taught in the whiteboard is going to be in a structured, and animations are used here, so it would be easier to visualize and understand. So first, what we did, we had the outputs from the patch embedding block. We are using that embedding, and we only take a patch of embedding. Let's take a patch of embedding. Okay, what we do, we project it into query, key, and value vectors, right? We are multiplying here with wq, wk, wv. We are getting query, key, and value vectors. Okay, like I said in the whiteboard explanation as well. Then what we do a scale attention. The formula this: softmax query times key divided by root dk times vz. We do the scale dot product attention. And what do we do after attention? We do that for all the patches in parallel, like I said in the matrix format. It's everything. We just did the example above was for a single row. We are doing it for a single row, but now we are doing it for all at once. This is parallel processing. And after that, I told you about uh, the simple process won't be enough, because we want the model won't be able to get perspectives from different dimensions, so we need to introduce multi-head attention. In multi-head attention, we split the query, key, and value vectors into h heads, and we use it for the calculations like before. Head, these are heads, and after that we concatenate the results from all the heads and multiply it with a learnable matrix that would give us a summarized embedding from all the different perspectives the model has been trained. And so this is the full multi-head pipeline. We had patch embeddings, we split it into heads, and each head, query, key, and value are subjected to scale dot product attention. Then we would get outputs from each heads. We concatenate the outputs of heads. Then we multiply or project it with learnable matrix, so that we obtained the vector of summarized vector from all the different perspectives of the D model shape. then we would get the contextual embedding. So this was for today's class. If you have any questions, please drop those questions in the comment section. Don't forget to like and subscribe to the channel. In the next class, we will be learning about the final inference and the multi-layer perceptron, residual connections, and how does a visual transformer actually predicts whether the given image is a cat or a dog. So thank you everyone. Have a great time.